Did you go to Newton, Dawson? Christian? Newton? Wichita. Ooh, you went so far. Then you go from going nowhere to going to Newton to going to Wichita. You forgot. Did you forget about that? Where'd you go on? Colorado. Anyone want to go further than Colorado? Minnesota. I'm glad you came back.
I went to Spain. I was very hungry. They didn't have anything on the plate. Yeah. So you had to taste. You know, I think Christian yesterday. I'm not doing on Friday. I watched you go to work. Oh yeah. He was driving around with me. Decided to come back over. What do you think? Oh yeah, what's the magic word?
Alright, how did it get to be that time already? Okay. Oops.
How do you figure what the Saturday?
Christian, notes? No. Okay, so quadratic function, this is what we're working with. Quadratic functions, any function of the form f of x equals ax squared plus bx plus c. A, B, and C are numbers, the x's are the variables. Or f of x equals a times the quantity x minus h plus k. This first one is written in what they call standard form. The second one is written in vertex form. Okay, so first one standard form, second one vertex form. What's a vertex? Heard that term before? Think geometry shapes. Triangle. Triangle has 3 vertices.
So where lines connect?
Kind of corners. Points of change where you change direction. Oops. Okay. So if you're in standard form, the ax squared is called your quadratic term. Ax squared is your quadratic term. What's the coefficient of x squared? The word coefficient. If it's ax squared, the coefficient of x squared would be the a. Coefficient is the number in front of a variable. Number in front of the variable. So the coefficient of x squared would be the a. The a is going to be, help us graph these a lot. If I cover up the quadratic term, I'm left with bx plus c. What kind of a graph is that? Linear. So we call the bx the linear term. So b times x is linear. And if I cover both of those up, what am I left with? And if you just have a number, the name of that type of function, it also starts with the c. Say it again, Logan. Constant. It's a horizontal line. So we have a quadratic term. What makes it a quadratic? We have a linear term, and we have a constant term. All right, so down below this one, we're going to fill in on someone, guys, fill in a little bit. I'm just going to draw a quick little parabola. So, happy little parabola. So there's a parabola. And then I'm going to put a point clear down at the bottom. So that point is where the graph, now don't get, on the left-hand side, you see how this arrow goes up? But the graph is doing what on this side? Is the graph increasing or decreasing? Okay, decreasing. Even though the arrow goes up, you look left to right, and as we go left to right, the graph is dropping. So we're decreasing here. Then at this point, I no longer am decreasing, but I am increasing. So we change directions, so guess what we call this point? The vertex. Okay.
So it doesn't have to finish like it.
No.
It can be a curve.
It's a curve in this case, yes. Because if you look at just the vertical component, we're dropping, 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 dropping. We stop dropping and we start going up. So if you take the x out of it, we just have the y. That's what it does. Okay, I'm going to draw a vertical line straight through my vertex. And it's going to be dashed. Does that vertical line split the parabola in two? Okay, so we could spin our parabola on that line, and it would just spin around, right? So what do we call a line that goes through something that something can spin on? The Earth has one. Axis. Good. So this right here is called the axis of symmetry. So we have an axis of symmetry. The graph is called a parabola. Let's write that down in case you didn't remember that. So the graph itself is a parabola. What am I going to call this part right there on the y-axis? What do we call the point where a graph crosses the y-axis? Y-intercept. So we have a y-intercept. Y-intercept is easy. It has one single name. But here, these 2 points these are going to be a little bit, these are kind of critical. We're going to spend a lot of time working with these little points right here. So if these are on the x-axis, these are called the, So these are called the x-intercepts. These are going to have lots of names. These are also called the roots. They're called the zeros. They're called the solutions. All of those names will show up. They all mean the x-intercepts. The roots of the function, the zeros of the function, the solutions to the equation, you're always looking for the x-intercept in that case. And we're going to spend a good portion of this chapter going over how to find those x-intercepts on different types of quadratics. Okay? Would you say this parabola that we drew, is it opening up or opening down? Which direction are the ends going? Up. So we say this opens up. Think of the bowl opening up. Okay? So underneath, I'm going to say graph opens up if okay, let's look back at the linear functions. What does the slope tell us on a linear function? if we're graphing a linear function, what does the slope tell us as far as whether the graph is... If it's positive, does the graph go up? If it's negative, the graph goes down. So here's our linear term, but we have something more powerful than a linear term. We have a quadratic term now. An x squared is going to be more powerful than an x, because if you have x to be 100, 100 squared is a lot more than just 100. So now the b, this b right here is not the king or queen of this, more the queen. Okay, ruling the roost here. So we're looking at the a. So if a is paired with the x squared, okay, the x squared might be the king, he might be the head honcho in charge, but the a is going to control where the king goes. So the a is the queen. Alright? Get used to that, guys. So, this x squared is the king of this graph, but it goes up only because a is going to be positive or negative if you're going up. Positive. So we say only if a is greater than or equal to 0. That is positive.
Should there be an equal sign under the A?
No. Good question. Because if a equals 0, do you have an x squared? No. So a has to be something other than 0 to have a quadratic graph. Okay? So what happens if a is negative? It goes down. Okay? So, it goes down. Here we have a vertex. That's the only thing I'm going to put on there. This is going to tie into vertex form. The reason it's called vertex form is it tells you the ordered pairs of h and k. And we're going to see this more later. We won't see this a lot right now. But vertex form, if you have an equation in vertex form that looks like that, you have the vertex, and that's going to be kind of a critical point. So, on this one right here, if a is less than 0, our graph is going down. Do I have a minimum? Minimum is the lowest value. Okay. So, we're thinking of a minimum as a floor. Do I have a floor on this graph? Do I have a ceiling? Yes. So, do I have a maximum? Yes. Okay. So, if a is less than 0, you have a maximum. Maximum. What did I just do? Maximum. That looks weird. I put a P there for some reason. And on this other one, if it's opening up, do I have a ceiling?
No.
No. It's going up forever. There's no ceiling, but do I have a floor? So I have a minimum. And these two things right here, the maximum, minimum, that is the y value of the vertex. The y value of the vertex. Now what we'll need today is in standard form. Standard form is not vertex form because it doesn't tell you the vertex right away, but there's formulas for it. I'm going to tell you the formulas. I won't tell you how you get them unless you really want to know. So if you're in standard form, you see how I use h and k for the vertex? Oh, sorry, going too quick. Get this down, then we'll start doing some practice so you know how to graph these. So if you're in standard form, use a formula you're going to want to know. Your h value, h is the vertex, so h is the x value of the vertex.